Have you ever gazed up at the night sky and felt a strange sense of motion, as if the universe itself is pulling you toward something unseen? It's not just your imagination. Across the vast expanse of space, galaxies are racing toward a mysterious force, defying everything we thought we knew about the cosmos. This isn't science fiction, it's real, and it's happening right now. Hidden in the darkness, an invisible colossus known as the Great Attractor is bending the fabric of the universe, drawing entire galaxies into its gravitational grip. But what is it? Where did it come from? And why does it wield such unimaginable power over everything around it? For decades, scientists have been piecing together clues, trying to unravel the secrets of this cosmic anomaly. Picture this: billions of stars, entire galaxies, all drifting like leaves caught in a silent river, pulled toward a point we can't even see. The Great Attractor sits like a phantom in the cosmic shadows, hidden behind the dense curtain of our own Milky Way. Its presence is felt, not seen, a gravitational whisper that tugs at the very foundations of space. But here's the chilling part: we still don't know what's really there. Is it a massive cluster of galaxies, a supermassive black hole beyond comprehension, or something even stranger, something our current understanding of physics can't explain? This is more than just a scientific curiosity. It's a window into the hidden forces shaping our universe. The Great Attractor challenges everything we thought we knew about gravity, motion, and the fate of the cosmos itself. And today, we're going on a journey to explore its mysteries, from the first puzzling observations to the cutting-edge theories trying to crack its code. By the end of this video, you'll see the night sky differently, because once you know about the Great Attractor, you'll never look up at the stars the same way again. So buckle up, we're about to dive into one of the universe's greatest enigmas. The discovery of the Great Attractor sent shockwaves through the scientific community when astronomers first noticed something strange in the 1970s. While mapping the motion of galaxies, they realized something extraordinary: entire clusters of stars weren't just drifting randomly through space. They were all moving in the same direction, as if tugged by an invisible hand. This mysterious force, hidden roughly 150 million light-years away in the direction of the Centaurus and Hydra constellations, defied every expectation. At first, scientists thought it might be a simple misreading of the data, but the more they studied it, the clearer it became. This was no ordinary cosmic structure. The Great Attractor is so massive that its gravity bends the paths of galaxies millions of light-years around it, pulling them inward like a cosmic whirlpool. Imagine dropping a handful of marbles onto a stretched-out sheet. They'd all roll toward the deepest dip. That's exactly what's happening on a galactic scale, except we still can't see what's causing the dip. What makes this even stranger is our own place in this celestial tug-of-war. The Milky Way, along with our neighboring Andromeda galaxy and countless others in the local group, is caught in this relentless pull. We're moving toward it at an astonishing speed of over 2 million kilometers per hour, faster than most spacecraft ever launched from Earth. And yet, because the Great Attractor lies behind the thick dust and stars of our own galaxy's central plane, it remains shrouded in mystery. This isn't just a question of some hidden cluster of matter. The Great Attractor challenges the very foundation of how we understand gravity and large-scale cosmic movement. According to our current models, galaxies should be spread out more evenly in the universe, not funneling toward one specific point. Some theories suggest it might be an unimaginably dense knot of dark matter, while others speculate it could be part of an even larger structure, a supercluster of galaxies with gravity so immense it warps space itself. Whatever the truth, one thing is certain: the Great Attractor is forcing us to rethink the rules of the cosmos. To grasp the sheer enormity of the Great Attractor, think of our Milky Way, a vast spiral of hundreds of billions of stars stretching 100,000 light-years from end to end. Now imagine not one, not 100, but tens of thousands of Milky Ways, all crushed together into a single, unfathomable mass. That's the scale we're dealing with. The Great Attractor isn't just big, it's a gravitational titan, a cosmic vacuum cleaner pulling everything toward it with a force that defies comprehension. Scientists estimate its mass could be anywhere from 10,000 to 50,000 times greater than our entire galaxy. To put that in perspective, if the Milky Way were a single grain of sand, the Great Attractor would be a boulder the size of a house. And its influence doesn't stop at its immediate vicinity. Like ripples from a stone thrown into a pond, its gravitational reach extends across hundreds of millions of light years, warping the paths of galaxies far beyond what we'd expect from visible matter alone. But here's where it gets even wilder. The Great Attractor isn't acting alone. It's part of something even larger, a mind-bending structure known as the Laniakea supercluster, a sprawling web of galaxies spanning 500 million light-years. Within this cosmic metropolis, the Great Attractor serves as a gravitational anchor, the heart of a vast celestial highway where galaxies flow like rivers into a common center. Picture a colossal whirlpool in space with entire galaxies spiraling inward in slow motion over billions of years. Yet the most unsettling part, we still can't see most of it. The Great Attractor's core is obscured by thick clouds of dust and stars in our own galactic backyard, making it nearly impossible to observe directly with optical telescopes. It's like standing behind a waterfall and trying to spot what's on the other side. You know something massive is there, but the view is frustratingly blurred. That's why astronomers rely on infrared and radio waves to pierce through the cosmic veil, revealing hints of galaxy clusters and dark matter weaving an invisible scaffold around this enigmatic giant. What's truly fascinating is how this discovery upended our understanding of cosmic order. For centuries, we assumed the universe was relatively uniform, with matter spread evenly like flour sifted across a table. But the Great Attractor proved there are hidden concentrations of mass so dense they rewrite the rules of motion on the grandest scales. Galaxies aren't just drifting, they're racing towards something, caught in a gravitational current we're only beginning to map. And as we peer deeper into this mystery, one question lingers. If the Great Attractor is pulling us, what's pulling it? Here's the cosmic irony. One of the most powerful forces in our universe is hiding in plain sight, masked by the very galaxy we call home. The Great Attractor sits in what astronomers call the zone of avoidance, a poetic name for a frustrating reality. This region of space lies directly behind the dense, dusty plain of the Milky Way, where stars, gas, and interstellar debris pile up like a celestial curtain. From our vantage point, it's like trying to spot a mountain through a blizzard. The light from distant galaxies gets absorbed or scattered by all that cosmic clutter, leaving us blind to what's pulling us toward it. But humanity has never been one to accept invisibility as an answer. That's where infrared and radio astronomy come in. Unlike visible light, these wavelengths can slip through the dust like whispers in the wind. Infrared telescopes, like the legendary Spitzer Space Telescope, detect the heat signatures of objects obscured by galactic fog. Radio telescopes, on the other hand, catch the faint signals emitted by hydrogen atoms, the universe's most abundant element, revealing hidden structures through their subtle radio whispers. Through these eyes, we've begun to map the unseen. Imagine peeling back layers of an ancient painting to find a masterpiece beneath. Slowly, scientists have uncovered hints of massive galaxy clusters lurking behind the Milky Way's veil, their combined gravity warping space-time like a hidden hand pressing down on a mattress. One of the most startling revelations, the Great Attractor might not even be the end game. Beyond it lies something even more colossal, the Vela supercluster, a sprawling network of galaxies adding yet another layer to this cosmic tug-of-war. Yet for all our ingenuity, the heart of the mystery remains just out of reach. We know the Great Attractor's pull is real because we can see galaxies bending toward it like trees in a hurricane. But the exact nature of what's doing the pulling, whether it's a dense knot of dark matter, a supercluster we've yet to fully map, or something even stranger, still eludes us. It's a humbling reminder that even in an age of space telescopes and supercomputers, the universe still keeps its deepest secrets close. Just when we thought the Great Attractor was the universe's best-kept secret, astronomers stumbled upon something even more baffling, a phenomenon so strange it's been dubbed dark flow. Picture this, not just one or two galaxies, but entire clusters of them, all drifting in the same direction like leaves caught in a cosmic river. This isn't just movement, it's a synchronized march toward the Great Attractor and beyond, at speeds that shouldn't be possible under our current understanding of the universe. Dark flow was first detected in 2008, when scientists studying the cosmic microwave background, the faint afterglow of the Big Bang, noticed something unsettling. Galaxy clusters millions of light-years apart were all hurtling toward the same patch of space, as if pulled by something far more powerful than the Great Attractor alone. The kicker, according to standard cosmology, the universe's expansion should be uniform, with matter distributed evenly enough that no single direction should dominate. Yet here we are, watching countless galaxies defy the rules, drawn toward some unseen force like iron filings to a magnet. What could possibly explain this? One theory suggests that dark flow might be evidence of structures outside our observable universe, regions so distant their light hasn't had time to reach us in the nearly 14 billion years since the cosmos began. Imagine standing on the shore of an ocean, watching waves roll in from a storm you can't see over the horizon. That storm could be a supermassive concentration of matter, so enormous its gravity tugs on everything in our visible universe. Some researchers even speculate it might be the gravitational imprint of another universe entirely, brushing against ours in ways we're only beginning to detect. But here's the twist: dark flow isn't just pulling things toward the Great Attractor. It's as if the attractor itself is caught in this current, dragged along by something even more colossal. This raises a spine-tingling question. What if the Great Attractor isn't the end of the chain, but just one link in a vast, invisible web of cosmic structures we've yet to map? The unsettling truth is that dark flow challenges the very foundation of modern cosmology, forcing us to confront the possibility that our universe is far stranger and far more interconnected than we ever imagined. And the mystery only deepens when you consider the numbers. These galaxy clusters are moving at speeds of up to 1,000 kilometers per second faster than any known force in our universe should allow. No amount of visible matter, not even the Great Attractor's staggering mass, can fully account for this motion. That leaves us with two options. Either our models of gravity and cosmic structure are missing a critical piece, or there's something out there, something beyond our current comprehension, exerting a pull so vast it reshapes the motion of the cosmos itself. So what does this mean for the fate of our universe? If dark flow is real and galaxies are being funneled toward some unimaginable destination, it could rewrite our understanding of everything from the Big Bang to the ultimate fate of space and time. Are we witnessing the early stages of a cosmic collision with another universe? Or is this the faint trace of a force so ancient it predates existence as we know it? The answers, much like the phenomenon itself, remain just out of reach, hidden in the dark currents of an expanding universe we're only beginning to navigate. Here we stand at the crossroads of cosmic forces, caught between two titanic powers shaping the very fabric of reality. On one side, the Great Attractor's immense gravity pulls galaxies together in a slow-motion collapse. On the other, dark energy, the universe's mysterious anti-gravity, pushes everything apart in an unstoppable expansion. These opposing forces aren't just abstract concepts, they're locked in an eternal tug of war that determines the fate of everything we see in the night sky. Picture the universe as a sheet of rubber stretched tight. the Great Attractor is like a heavy weight placed on that sheet, creating a deep depression that draws nearby objects inward. Now imagine someone gripping the edges of that same sheet and pulling outward with relentless force. That's dark energy at work. While the Great Attractor operates on scales of hundreds of millions of light years, dark energy works everywhere at once, stretching the very space between galaxies. What makes this battle so fascinating is how unevenly these forces play out. Within galaxy clusters and superclusters like Laniakea, gravity still dominates. That's why we see the Milky Way and our neighboring galaxies all streaming toward the Great Attractor. But zoom out far enough and dark energy wins every time, accelerating the expansion of space itself. Scientists first uncovered dark energy in the late 1990s when they discovered something shocking. The universe wasn't just expanding, it was doing so faster and faster over time. This defied all expectations, as gravity should have been slowing cosmic expansion down. Instead, some unknown force, now called dark energy, was overpowering gravity on the grandest scales. Current estimates suggest dark energy makes up nearly 70% of the universe's total energy content, while all visible matter, stars, planets, galaxies, accounts for less than 5%. The rest, dark matter, another invisible player that amplifies gravitational effects but doesn't counteract dark energy's push. Here's where things get truly mind-bending. The Great Attractor and dark energy aren't just competing, they're reshaping space in fundamentally different ways. Gravity creates structure, pulling matter together to form galaxies, clusters, and superclusters. Dark energy erodes these connections, stretching space until distant galaxies vanish over the cosmic horizon. This means the Great Attractor's influence has an expiration date. Billions of years from now, as dark energy continues its work, even the mighty pull of this cosmic behemoth won't be enough to hold onto its galactic captives. Eventually, the space between galaxies will stretch faster than gravity can counteract, leaving the Great Attractor isolated in an ever-expanding void. Yet for now, we're in a brief cosmic sweet spot where both forces remain visible in their effects. We can watch galaxies flowing toward the Great Attractor while simultaneously measuring the universe's accelerating expansion. This rare window gives astronomers unprecedented insight into how gravity and dark energy interact, a real-time experiment unfolding across billions of light years. Some theories even suggest that dark energy's strength may change over time, meaning the balance between these forces could shift in ways we can't yet predict. What does this mean for the universe's ultimate fate? If dark energy continues to dominate, the cosmos faces a cold, lonely future where galaxies become invisible islands drifting apart in endless darkness. But if the Great Attractor represents a hidden pattern, if there are more such gravitational anchors woven through space, perhaps structure can persist far longer than we think. One thing's certain, as we peer deeper into this cosmic struggle, we're not just learning about distant galaxies. We're uncovering the fundamental rules that govern existence itself, written in the silent dance between attraction and repulsion, between the pull of the known and the push of the unknown. The universe isn't just a random scattering of galaxies, it's woven together in an intricate, sprawling tapestry known as the cosmic web. Picture a colossal neural network with threads of dark matter and glowing galaxies stretching across unimaginable distances, connecting clusters and voids in a delicate balance. At the heart of this vast structure, the Great Attractor sits like a cosmic crossroads, one of the universe's grand hubs where galactic highways intersect. It's not just pulling galaxies, it's anchoring an entire sector of this web, a gravitational linchpin in the architecture of the cosmos. To understand its role, imagine the cosmic web as a city subway system. Most galaxies ride along filamentary lines, streams of gas and dark matter flowing between voids, the universe's empty stations. But at certain points, these lines converge at bustling hubs where gravity gathers matter into dense knots. The Great Attractor is one of those hubs, a megalopolis in space where galaxies pile up like commuters at rush hour. And just as a major transit center shapes the flow of an entire city, this colossal node bends the paths of galaxies millions of light years around it, redirecting their motion like cosmic traffic control. What's truly astonishing is how perfectly the Great Attractor fits into this web. Observations show it's nestled within the Laniakea supercluster, a filamentary sprawl of galaxies spanning over 500 million light-years. Laniakea means immeasurable heaven, in Hawaiian a fitting name for a structure so vast, it makes even the Great Attractor seem like just one neighborhood within a metropolis. Here, galaxies stream along invisible highways of dark matter, all flowing toward the attractor's gravitational basin like rivers merging into a single, unstoppable current. But the cosmic web isn't static, it's alive with motion, a dynamic dance of attraction and expansion. While dark energy stretches the space between superclusters, gravity works tirelessly within them, pulling galaxies into these dense nodes. The Great Attractor is proof of gravity's enduring influence, a reminder that even in an accelerating universe, some structures hold fast, their sheer mass bending the rules of the cosmic game. And just beyond it, astronomers have spotted hints of even larger filaments, potential bridges to other superclusters, suggesting this web might extend farther than we've ever dared to map. Yet for all we've uncovered, the full picture remains tantalizingly out of reach. The cosmic web's filaments are made mostly of dark matter, an invisible scaffold we can only detect through its gravitational fingerprints. It's like trying to map a city at night by watching the movement of cars. You can trace the roads by their traffic, but the streets themselves stay shrouded in shadow. That's why projects like the Dark Energy Survey and future telescopes like the Nancy Grace Roman Space Telescope aim to chart these hidden pathways, peeling back the veil on the universe's true structure. What's become clear, though, is that the Great Attractor isn't an anomaly, it's a blueprint. Across the observable universe, similar nodes dot the cosmic web, each a gravitational anchor for its own supercluster. Some may be even more massive, hidden behind more distant veils of dust and stars. Together, they form a lattice of influence, a hidden framework guiding the universe's growth. And as we trace their connections, we're not just mapping space, we're uncovering the hidden blueprints of existence itself, written in the silent pull of matter we can't see but know must be there. Just when we thought the Great Attractor held all the answers, astronomers uncovered another gravitational heavyweight in the cosmic ring, the Shapley supercluster. Imagine two celestial giants locked in a silent tug of war, each pulling galaxies toward itself with unimaginable force. Located over 650 million light-years away in the constellation Centaurus, Shapley isn't just another cluster. It's one of the most massive concentrations of matter ever observed, a sprawling metropolis of galaxies so dense, its gravity might be the real puppeteer behind the mysterious dark flow we've been tracking. The Shapley supercluster is a behemoth even by cosmic standards. While the Great Attractor anchors the Laniakea supercluster, Shapley dwarfs it, containing dozens of galaxy clusters packed into a region spanning hundreds of millions of light-years. Picture a bustling megacity compared to a large town. That's the scale difference here. Some estimates suggest Shapley's mass could be 10 times greater than the Great Attractor's, making it a prime suspect for the unexplained pull on our local universe. But here's the twist: Shapley isn't just pulling galaxies toward it. It might be pulling the Great Attractor itself, like a hidden hand guiding the hand we can see. This revelation sparked a heated debate among scientists. Could Shapley be the true mastermind behind the cosmic motion we've attributed to the Great Attractor? The evidence is compelling. When researchers mapped the velocities of galaxies caught in this vast flow, they noticed something odd: the motion didn't stop at the Great Attractor. Galaxies kept streaming past it, as if something even farther away was calling the shots. Shapley, sitting perfectly in that line of movement, emerged as the likely culprit. It's as if we've been watching a river flow toward a waterfall, only to realize the waterfall itself is being pulled by an ocean beyond the horizon. Yet the mystery deepens when we consider the numbers. Even Shapley's staggering mass might not fully account for the extreme speeds of dark flow. Some galaxies are racing toward it at over 1,000 kilometers per second faster than gravity from visible matter alone should allow. This has led to wilder theories like the existence of undiscovered superclusters beyond Shapley, or even exotic physics like gravitational shadows from other universes. The unsettling truth, we might be staring at a cosmic Russian nesting doll where each layer we peel back reveals another, larger force at work. What makes this discovery so thrilling is how it reshapes our cosmic map. For decades, we assumed the Great Attractor was the dominant force in our galactic neighborhood. Now, we're realizing it might just be a waypoint in a far grander journey, one that stretches across hundreds of millions of light years toward the Shapley supercluster and perhaps beyond. It's a humbling reminder that the universe rarely fits into neat boxes. Just when we think we've found the answer, the cosmos reveals another layer, another mystery, another gravitational whisper urging us to look farther. And somewhere in that vast expanse, hidden behind curtains of dust and time, the next great cosmic surprise is waiting. Our journey through the cosmos isn't just a straight path. It's a delicate dance between titanic forces, a celestial tug of war where the Milky Way is the rope. On one side, the Great Attractor exerts its pull with the gravitational might of tens of thousands of galaxies. On the other, the Shapley supercluster tugs from 650 million light-years away, its mass so vast it could be dictating the motion of entire superclusters. Caught in the middle, our galaxy and its neighbors aren't simply drifting, they're navigating a cosmic battlefield where gravity's invisible threads stretch and snap in an endless contest of strength. Think of it like a game of interstellar seesaw. If you've ever watched two children balancing on a playground plank, you know the slightest shift in weight changes everything. Now imagine one child is the Great Attractor and the other is Shapley, each planting their feet firmly in the fabric of space-time. The Milky Way sits somewhere along that plank, constantly adjusting its trajectory as these colossal forces vie for dominance. Right now, we're moving toward the Great Attractor at 2 million kilometers per hour, but that motion isn't just its doing. Shapley's distant pull is likely amplifying the effect, adding extra speed to our cosmic commute. Here's where it gets even more fascinating. These forces don't just pull in straight lines, they bend the very space around them, creating gravitational currents that galaxies surf like ships caught in twin whirlpools. Picture steering a boat down a river where two powerful eddies compete for control. The water itself twists and churns, forcing you to adjust course constantly. That's what's happening to every galaxy in our local universe. Even as we're drawn toward the Great Attractor, Shapley's far-off grip subtly warps our path, like an unseen hand nudging the compass needle. Astronomers call this phenomenon bulk flow, the collective motion of galaxies caught in these competing gravitational fields. It's not just about which force is stronger, it's about how their combined influence sculpts the cosmic landscape over billions of years. The Milky Way isn't falling toward either attractor in a straight line. Instead, we're tracing a graceful arc through space-time, a trajectory shaped by the ever-shifting balance between these two giants and the dark energy stretching the universe apart beneath them. What's truly mind-bending is how this tug of war reveals the hidden architecture of the cosmos. The Great Attractor and Shapley aren't isolated anomalies, they're nodes in a vast network of gravitational influence, connected by filaments of dark matter we're only beginning to map. Every galaxy's motion is a clue, a breadcrumb leading us deeper into understanding how mass is distributed across scales we can barely comprehend. And just like a detective piecing together a crime scene from scattered evidence, scientists use these galactic trajectories to reverse engineer the universe's hidden scaffolding, one gravitational tug at a time. Yet the most humbling realization, this battle has an expiration date. As dark energy accelerates the universe's expansion, the space between superclusters will stretch faster than gravity can compensate. Eventually, even the mightiest attractors will lose their grip, their gravitational reach severed by the relentless expansion of space itself. The Milky Way and Andromeda may merge, our local group may collapse into a single galaxy, but beyond that, the currents we're riding today will fade into cosmic history, leaving future astronomers in an island universe with no memory of the giants that once ruled the sky. For now, though, we're living in a golden age of cosmic cartography, where every new telescope peels back another layer of this gravitational drama. The James Webb Space Telescope's infrared eyes, the upcoming Vera Rubin Observatory's sweeping surveys, each brings us closer to understanding not just where we're going, but how the universe itself engineers its grandest motions. And as we chart these invisible currents, we're not just mapping space. We're learning to read the universe's hidden language, written in the silent pull between attractors we can't see, but whose influence shapes everything we know. Einstein's theory of general relativity gives us the blueprint to understand the Great Attractor's overwhelming grip on the cosmos. Picture space-time not as a static stage, but as a dynamic, stretchable fabric, one that warps under the weight of mass and energy. When a massive object like the Great Attractor sits on this cosmic sheet, it doesn't just bend space-time, it twists the very paths that galaxies travel, forcing them into a cosmic river flowing toward its depths. This isn't just gravity as Newton imagined it, with simple forces acting at a distance. Relativity shows us gravity as geometry, where the shape of the universe itself dictates how everything moves. But modeling the Great Attractor's influence isn't as straightforward as plugging numbers into Einstein's equations. The real challenge lies in the sheer scale of this phenomenon. Most applications of relativity deal with single stars, black holes, or even galaxy clusters, objects we can observe directly. The Great Attractor, though, is a sprawling mess of thousands of galaxies, dark matter, and turbulent gas clouds, all tangled into a gravitational knot so complex, even supercomputers strain to simulate it accurately. It's like trying to predict every swirl in a hurricane while standing in the middle of the storm. You know the physics, but the chaos defies easy calculation. One of relativity's most startling predictions is that gravity isn't instantaneous. Changes in the gravitational field ripple outward at the speed of light, like waves spreading across a pond. This means the Great Attractor's pull isn't some static force. It's a dynamic interaction that evolves as galaxies move and collide within it. When we observe its effects on distant galaxies, we're seeing a snapshot of how its gravity propagated millions or even billions of years ago. In a sense, the attractor we're studying today might already be radically different from the one influencing us now, a cosmic delay that adds another layer of mystery to our calculations. Yet relativity also reveals where our theories hit their limits. The Great Attractor's behavior aligns with Einstein's predictions on large scales, but there are whispers in the data that don't quite fit. Some galaxies move faster than relativity alone should allow, hinting at unseen forces or even flaws in our understanding of gravity itself. Could there be corrections to Einstein's theory waiting to be uncovered in the attractor's shadow? Modified Newtonian dynamics (MUND), an alternative framework, suggests gravity might behave differently at cosmic scales, though most evidence still favors relativity. The Great Attractor serves as a testing ground for these ideas, a natural laboratory where the universe pits our best theories against its most extreme conditions. What makes this even more fascinating is how relativity intertwines with dark matter, the invisible scaffolding thought to amplify the attractor's pull. Einstein's equations don't care whether the mass-bending spacetime is visible stars or unseen particles. They treat all matter equally. This means the Great Attractor's true power might come from dark matter's hidden bulk, warping space in ways we can infer but never directly see. It's like mapping a city by watching how people flow through streets, even if the buildings themselves are cloaked in fog. As we push our understanding further, we're also confronting the boundaries of relativity itself. Near the attractor's core, where densities reach unimaginable levels, could quantum gravity effects normally negligible on cosmic scales start to play a role? Theories like loop quantum gravity or string theory suggest spacetime might fray or twist in new ways under such extremes. While we lack the tools to probe these regimes yet, the Great Attractor dangles a tantalizing possibility that hidden in its depths might be clues to a deeper, unified theory of gravity, one that bridges the cosmic and the quantum. For now, relativity remains our sharpest lens for deciphering this enigma. Every galaxy spiraling toward the attractor, every distortion in the cosmic microwave background is a testament to Einstein's enduring vision. A universe where matter tells spacetime how to curve and spacetime tells matter how to move. But the Great Attractor also reminds us that even our most brilliant theories are works in progress, and the cosmos always has another surprise waiting just beyond the edge of our equations. The cosmic microwave background, the faded glow of the Big Bang, holds secrets about the Great Attractor written in light older than the stars themselves. This ancient radiation, a snapshot of the universe just 380,000 years after its birth, carries faint imprints of density variations, places where matter was slightly more or less packed together. Today, those tiny fluctuations have snowballed into the vast cosmic web we see, with the Great Attractor sitting at one of its most crowded intersections. To understand how this works, picture the early universe as a placid pond disturbed by a single pebble. The ripples that spread outward aren't random, they follow patterns set by the pebble's impact. In the same way, the CMB's temperature variations, tiny hot and cold spots no larger than 1 part in 100,000 reveal where matter began clumping together under gravity's pull. Over billions of years, those over-dense regions grew into galaxy clusters, while under-dense zones stretched into cosmic voids. And right in the direction of the Great Attractor, astronomers have spotted something peculiar. A subtle but persistent dip in the CMB's temperature, as if the background radiation is being tugged out of shape by an unseen hand. This phenomenon, called the kinematic Sunyaev-Zeldovich effect, occurs when the CMB's photons interact with the hot gas in massive galaxy clusters. As these photons pass through the Great Attractor's gravitational field, they gain or lose energy, leaving telltale shadows in the microwave sky. It's like holding a flashlight behind a frosted window. If someone presses their hand against the glass, you'll see a dimmer spot where the light strains to pass through. The CMB cold spot near the Great Attractor suggests its gas clouds are moving en masse, dragging the radiation along with them in a way that aligns perfectly with our models of its gravitational pull. But the clues don't stop there. When scientists map the CMB's polarization, the orientation of its light waves, they've detected a large-scale swirling pattern that hints at something astonishing. The entire local universe, including the Great Attractor, might be moving in unison toward an even more distant structure. This aligns eerily with dark flow observations, suggesting the CMB isn't just a relic of the past, it's a dynamic record of how the universe's largest structures continue to evolve. The Great Attractor's fingerprint is there, but so is the shadow of whatever lies beyond it, a reminder that we're still only seeing part of the puzzle. What makes these CMB anomalies so powerful is their dual nature. They're both a window into the universe's infancy and a mirror reflecting its present-day architecture. The same ripples that seeded galaxy formation also set the stage for attractors like the one pulling us in today. And as next-generation telescopes like the Simons Observatory and CMB-S4 scan the microwave sky with unprecedented precision, we may finally uncover whether the Great Attractor is the end point of this cosmic river or just another bend in its current. To unravel the Great Attractor's mysteries, scientists are turning the universe into a digital playground, building colossal supercomputer simulations that recreate billions of years of cosmic evolution in mere weeks. These aren't just animated models, they're precision-engineered virtual universes where every galaxy, every wisp of dark matter, obeys the laws of physics as we understand them. The goal, to rewind the tape of time and watch the Great Attractor emerge from the chaos of the early cosmos, revealing whether our theories about its origins hold up under scrutiny. One of the most ambitious efforts, the Millennium Simulation, treated dark matter as the invisible scaffolding of reality. By programming in the known distribution of matter from the cosmic microwave background, researchers watched as gravity sculpted this digital universe over 13 billion simulated years. The result was eerie. Virtual galaxy clusters coalesced exactly where the Great Attractor sits today, pulled together by dark matter's relentless grip. But the simulation revealed something unexpected. The attractor isn't a singular monster. It's more like a gravitational echo, a focal point where multiple filaments of the cosmic web intersect, amplifying its pull far beyond what visible matter could achieve alone. Yet even the most sophisticated simulations hit snags. When astronomers compared these digital universes to real telescope data, they noticed discrepancies. The Great Attractor's observed pull is stronger than most models predict. This gap suggests either dark matter behaves in ways we haven't accounted for, or the attractor is fed by hidden reservoirs of mass simulations haven't yet included. Some teams are now testing radical ideas like warm, dark matter particles that move fast enough to smooth out small-scale cosmic structures while still forming massive hubs like the attractor. Others are layering in magnetic fields and turbulent gas dynamics, factors often simplified in early models but which might tip the balance toward reality. The real breakthrough came when simulations began incorporating dark energy's accelerating push against gravity's pull. These cosmic tug-of-war models show how the Great Attractor, while formidable, is fighting a losing battle against the universe's expansion. Over billions of years, dark energy will stretch the space between superclusters so vast that even the attractor's gravity can't hold its galactic empire together. For now, though, these digital laboratories let us test scenarios impossible to observe in real time, like what happens when two supercluster cores collide, or how dark matter's hypothetical filaments channel galaxies toward the attractor like raindrops down a windowpane. What's emerging from these virtual experiments is a humbling truth. The Great Attractor isn't an anomaly, it's a cosmic inevitability. Wherever dark matter clumps densely enough, gravity weaves it into knots that dominate their corners of the universe. Our Milky Way's fate to be drawn inexorably toward this invisible leviathan is just one thread in a tapestry of motion playing out across the cosmos. And as supercomputers grow more powerful, they're not just solving the attractor's riddle, they're showing us how the universe builds its largest structures, one gravitational whisper at a time. If the Great Attractor is the heart of our cosmic neighborhood, then the Laniakea supercluster is its sprawling body, a web of galaxies so vast it redefines our sense of place in the universe. Stretching over 500 million light-years and containing more than 100,000 galaxies, Laniakea isn't just a structure, it's an entire ecosystem of motion, with every star system caught in its slow gravitational dance. The name itself, Hawaiian for immeasurable heavens, captures the sheer scale of this celestial metropolis, where the Great Attractor serves as the bustling downtown, and galaxies like ours are mere commuters flowing toward its center. Picture Laniakea as a colossal watershed with galaxies instead of rivers. Just as water trickles down mountains into valleys and eventually merges into mighty rivers, galaxies slide along invisible filaments of dark matter, funneling toward the Great Attractor's gravitational basin. The Milky Way resides in a quieter suburb of this supercluster, part of a smaller group called the Local Group, which itself orbits within Laniekea's grander flow. But here's what's mesmerizing. This isn't random drift. Every galaxy within Laniakea shares a destiny, drawn toward the same focal point like iron filings pulled toward a magnet. Zoom out far enough and Laniekea's structure becomes breathtakingly clear. It resembles a cosmic jellyfish with tendril-like filaments of galaxies streaming inward, all converging toward the Great Attractor's dense core. Hubble's law tells us the universe is expanding, with galaxies generally moving apart, but within superclusters like Laniakea, gravity overrules that expansion, binding galaxies together in a shared motion. This creates a surreal duality. While the universe as a whole stretches outward, our local patch is crisscrossed with these rivers of galaxies, all flowing against the cosmic tide. Yet Laniakea isn't an isolated island. It borders other superclusters like Shapley and Perseus Pisces, each with its own gravitational anchors. The boundaries between them aren't sharp borders, but zones where galactic currents subtly shift direction, like weather fronts between atmospheric systems. Recent studies suggest Laniakea might even be part of an even larger structure, a supercluster that could rewrite our maps of the universe once again. It's a humbling reminder that the more we explore, the more we realize how much is still uncharted. What makes Laniakea so pivotal is how it reframes our cosmic address. For centuries, we saw Earth as the center of creation, then the Sun, then the Milky Way. Now we understand we're part of something far grander, a supercluster where the Great Attractor acts as the unseen conductor, orchestrating the motion of galaxies on scales once unimaginable. And as we peer deeper into this galactic web, we're not just mapping space. We're learning how gravity writes the story of the universe, one filament, one galaxy, one irresistible pull at a time. The Great Attractor has eluded us for decades, hidden behind the Milky Way's dusty veil, but humanity's next generation of telescopes is about to lift the cosmic curtain. Imagine trying to study a mountain range through dense fog, only for the mist to suddenly clear, revealing peaks you never knew existed. That's the promise of instruments like the James Webb Space Telescope and the Square Kilometre Array, poised to pierce the zone of avoidance and expose the attractor's secrets with unprecedented clarity. Webb's infrared eyes are tailor-made for this challenge. While optical telescopes see only the starlight blocked by galactic dust, Webb detects heat, the warm glow of stars and galaxies shining through the obscuring clouds. It's like swapping out a flashlight for night vision goggles. Already, Webb has teased glimpses of previously hidden galaxies lurking behind the Milky Way's bulge, their distorted shapes hinting at the gravitational maelstrom around the attractor. With each new observation, we're assembling a puzzle where half the pieces were missing, revealing how galaxies cluster and warp under forces we've only guessed at until now. But Webb isn't working alone. On the ground, the Square Kilometre Array, a sprawling network of radio antennas across 2 continents, will map the attractor's dark matter skeleton by tracing the faint radio whispers of hydrogen atoms. Hydrogen is the universe's most abundant element, and its emissions act like cosmic breadcrumbs, marking where invisible dark matter's gravity has herded gas into filaments and knots. The SKA's sensitivity is staggering. It could detect a cell phone signal from a planet orbiting a star halfway across the universe. When trained on the attractor, it won't just show us hidden galaxies, it'll chart the gravitational tides between them, exposing how dark matter weaves this entire region together. Then there's the Vera Rubin Observatory, set to begin its 10-year legacy survey of space and time in 2025. With a camera the size of a small car, Rubin will capture the entire southern sky every few nights, spotting subtle changes in galactic motion that could reveal the attractor's true scale. Think of it as time-lapse photography for the cosmos. By tracking how galaxies subtly accelerate over years, we'll measure the attractor's gravitational fingerprint with precision never before possible. Combined with gravitational wave detectors like LISA, which may sense ripples from supermassive black holes near the attractor's core, we're building a toolkit to study this enigma in every wavelength and dimension. What's thrilling is how these tools complement each other. Webb's infrared vision exposes the attractor's visible structure, while SKA's radio maps reveal the dark matter scaffolding holding it up. Rubin tracks its motion, and LISA listens for the collisions powering its heart. Together, they'll transform the attractor from a shadowy silhouette into a three-dimensional portrait, one that might solve lingering mysteries, like why some galaxies near it move faster than our models predict. Are we missing a hidden reservoir of mass, or is there something fundamentally new about gravity in these extreme environments? The answer could redefine cosmic cartography. If upcoming observations confirm that dark flow stretches beyond the attractor toward Shapley or other superclusters, we may need to redraw our maps entirely, not as isolated islands of galaxies, but as interconnected currents in a vast cosmic ocean. And with the European Space Agency's Euclid mission joining the hunt, mapping dark matter's distribution with razor-sharp precision, we're on the verge of seeing the universe's hidden architecture not as theory, but as revealed truth. This isn't just about solving a scientific puzzle. Peering behind the Milky Way's curtain means glimpsing a sector of the universe we've never truly seen before, a region that's been tugging at us for billions of years without showing its face. Within the decade, the Great Attractor won't be so great or mysterious anymore. It'll become familiar terrain, its secrets laid bare by technology that turns the invisible into the visible and the unknown into the understood. And when that happens, we won't just know where we're being pulled, we'll finally see the hand that's been pulling us all along. While the leading theories explain the Great Attractor through dark matter and galaxy clusters, some scientists dare to ask, what if it's something far stranger? Beyond conventional astrophysics lies a realm of wild possibilities, exotic phenomena that could rewrite the rules of gravity itself. Take primordial black holes, hypothetical remnants from the universe's first second. These aren't your average black holes formed from dying stars. They're thought to have spawned in the chaotic heat of the Big Bang, with masses ranging from a mountain to thousands of suns. Now imagine a swarm of them, an invisible hive of these ancient predators clustered together, their combined gravity mimicking a single colossal mass. Unlike dark matter, which spreads diffusely, primordial black holes would concentrate gravity in dense, invisible knots, potentially explaining why the Great Attractor's pull seems so sharply focused despite our inability to see its source. Then there's the even more radical idea of modified gravity. What if our understanding of Einstein's relativity breaks down at cosmic scales? Theories like modified Newtonian dynamics suggest gravity behaves differently when extremely weak, like in the vast spaces between galaxy clusters. Instead of invoking dark matter, proposes tweaks to gravitational equations that could account for the Great Attractor's pull without needing unseen mass. While most observations favor dark matter's existence, anomalies in galactic motions keep this debate alive. Picture trying to navigate with an outdated map. Sometimes the terrain just doesn't match the lines. The Great Attractor might be one of those places where our cosmic map needs redrawing. But the most mind-bending hypothesis, the Great Attractor could be a cosmic texture, a flaw in spacetime's fabric left over from the universe's violent birth. Think of spacetime as a frozen lake. Most of it is smooth, but if the water froze unevenly, cracks or ridges might form. These hypothetical textures would warp gravity around them, creating phantom masses where none truly exist. It's a long shot, but if true, it would mean the attractor isn't a thing at all, just a wrinkle in reality's canvas, tricking galaxies into converging where nothing actually waits. Of course, these ideas sit on science's fringes for a reason. Extraordinary claims require extraordinary evidence, and so far, dark matter and superclusters explain most observations cleanly. Yet the Great Attractor's lingering mysteries, like why some galaxies near it move faster than predicted, leave just enough room for wonder. Perhaps the truth blends the conventional and the bizarre, a dense cluster of galaxies amplified by dark matter, threaded with a few primordial black holes, all bending space-time in ways we're only beginning to model. Until we peer deeper behind the Milky Way's curtain, one thing's certain: the universe keeps its greatest puzzles just out of reach, teasing us with clues that defy easy answers. The Milky Way's journey toward the Great Attractor isn't a straight shot, it's a cosmic odyssey with an uncertain ending. Right now, our galaxy is racing toward this gravitational behemoth at over 2 million kilometers per hour, caught in a current that's been pulling us in for billions of years. But here's the twist: we might never actually reach it. The universe is expanding faster than gravity can keep up, and dark energy's relentless push could stretch space so much that even the Great Attractor's pull becomes irrelevant. It's like trying to swim toward a distant island while the ocean itself keeps widening beneath you. Current projections suggest the Milky Way and the Great Attractor are locked in a delicate dance between attraction and expansion. Based on their relative motion, we'd theoretically merge with the attractor's core in about 150 billion years, but that's assuming dark energy doesn't interfere. In reality, long before we get close, the accelerating expansion of the universe will likely stretch the space between us until the attractor's gravity can no longer reel us in. Imagine two ants crawling toward each other on a rubber band. If someone starts stretching the band faster than the ants can crawl, they'll never meet. That's the fate awaiting our galaxy, forever inching toward a destination that keeps slipping further away. But the story doesn't end there. While the Great Attractor may remain out of reach, its gravitational influence is still shaping our local universe in profound ways. Over the next few billion years, the Milky Way and Andromeda will collide, forming a new elliptical galaxy astronomers call Milkomeda. This merged giant will continue drifting toward the attractor, along with dozens of other galaxies in our local group. For a time, gravity will dominate locally, binding nearby galaxies together even as the broader universe expands. It's like being in a lifeboat with others. You might drift apart from distant ships, but your little group stays tightly knit. The real wild card is dark energy's strength over time. Some theories suggest its influence could weaken or even reverse, allowing gravity to regain the upper hand. If that happens, the Great Attractor might still claim us after all. Other models propose dark energy grows stronger, tearing apart galaxy clusters and even atoms themselves in a Big Rip scenario. In that case, the attractor would vanish from our cosmic horizon long before we felt its full pull. What's certain is that the Milky Way's fate hinges on this invisible tug of war. A battle between the universe's two most powerful forces, with our galaxy caught in the middle. One thing's clear: the Great Attractor has already left its mark on us. Even if we never reach it, its gravity has set our trajectory for eons, steering the Milky Way through the cosmic web like a ship guided by invisible tides. And as we peer deeper into this mystery, we're not just mapping our future, we're uncovering the hidden forces that sculpt the universe itself, one gravitational whisper at a time. If you could stand at the edge of the Great Attractor's gravitational influence, you'd witness one of Einstein's strangest predictions playing out in real time. Time itself would stretch and slow like taffy pulled to its limit. Near an object this massive, where gravity warps space-time into a steep well, clocks tick slower than those in the emptier voids between galaxies. This isn't science fiction, it's relativity in action. A star orbiting close to the attractor's core might experience a single hour while thousands of years pass for an observer far away in intergalactic space. The difference would be subtle over short periods, but across millions of years, entire cosmic epochs could diverge between the attractor's heart and the outskirts of its influence. Imagine two astronauts, one stationed near the Great Attractor, the other drifting in the relative calm of our local group. If they could compare watches after a century, the attractor-bound clock would lag behind, its hands crawling through seconds as if weighed down by invisible fingers. This time dilation isn't just theoretical. We've measured it on Earth's surface, where gravity is weak but still strong enough to make clocks tick slower at sea level than on mountaintops. Now multiply that effect by thousands of galaxies worth of mass, and you begin to grasp the distortion possible near the attractor's core. Light struggling to escape its grip doesn't just lose energy, it stretches into longer, redder wavelengths, a phenomenon called gravitational redshift. But here's where it gets even stranger. If we could observe a galaxy deep within the attractor's grip, its light wouldn't just be redshifted, its very evolution would appear to move in slow motion from our perspective. Supernova might take longer to brighten and fade, star formation could seem to crawl, and even the spin of galaxies might look lethargic compared to identical systems farther from the attractor's pull. It's as if the universe hits the brakes near such extreme gravity, stretching moments into eons for distant observers. This cosmic time warp isn't just a curiosity, it complicates how we study the attractor itself. When we peer at galaxies near its core, we're not just seeing them as they were billions of years ago due to light's travel time, we're seeing their clocks run slower than ours. A supernova explosion observed there might unfold over weeks instead of days, its light curve artificially stretched by relativity's grip. Astronomers have to account for this when measuring motions or ages, untangling the effects of time dilation from the actual physics playing out in these extreme environments. And the implications ripple outward. If the Great Attractor hosts supermassive black holes, likely anchors in its densest regions, their event horizons would be surrounded by spacetime stretched so thin, time nearly grinds to a halt. Matter spiraling into these black holes wouldn't just vanish. From our distant vantage, it would appear to freeze at the edge, its last signals redshifted into oblivion. This creates a paradox. The more massive and dense the attractor's core, the harder it becomes to observe what's happening there in real time. We're left studying ghosts of events, their timelines warped by gravity's relentless grip. Yet this distortion might also be a tool. By measuring how much time slows in the attractor's vicinity, we could map its true mass distribution with unprecedented precision. Subtle differences in redshift across galaxies could reveal hidden concentrations of dark matter or even exotic objects like primordial black holes lurking in its depths. It's like listening to a symphony where every instrument is slightly out of sync. The discord itself tells you where the unseen players sit. What's both humbling and thrilling is that these relativistic effects aren't confined to the attractor. Every massive structure in the universe bends time in its own way, creating a patchwork of temporal currents swirling through the cosmos. We're all swimming in this river, our clocks ticking at different rates depending on where we stand. The Great Attractor just happens to be one of the mightiest whirlpools in that stream, a place where time doesn't just bend but nearly buckles under the weight of gravity's hand. For civilizations of the distant future, the Great Attractor wouldn't just be a cosmic curiosity, it would be the ultimate navigational hazard. Picture a starship crew charting a course across intergalactic space, only to realize their destination lies against the universe's strongest current. Escaping the attractor's pull would demand energy reserves beyond anything we can fathom today. Just breaking free from Earth's gravity requires rockets burning thousands of tons of fuel. Now scale that up to galactic proportions. The kinetic energy needed to resist the attractor's drag would dwarf the total output of every star in the Milky Way combined. Future engineers might harness black hole reactors or dark matter annihilation technologies that sound like science fiction now, but would be survival necessities for any civilization trying to swim upstream in this cosmic river. But energy alone isn't the only hurdle. The sheer time involved makes this an existential challenge. even at near light speeds, crossing the void between galactic clusters takes millions of years. A voyage aimed away from the attractor would face relentless deceleration, like hiking up an ever-steepening slope. Generations of explorers would watch helplessly as their velocity bled away, siphoned by invisible gravitational tides. Entire civilizations might rise and fall aboard these ships before they gained enough distance to break free. Some might abandon the struggle entirely, choosing instead to ride the current toward the attractor's heart, a one-way journey into the universe's densest unknown. And what if the attractor's pull isn't uniform? Its core likely swirls with chaotic gravity wells from colliding galaxy clusters and supermassive black holes. Navigating that maze would be like sailing through a hurricane's eye wall, where gravitational eddies could fling ships off course or tear them apart. Advanced civilizations might deploy space-time altering tech, imagine gravity lenses that bend the attractor's own pull against itself, or warp bubbles shielding ships from tidal forces. Yet even these hypothetical solutions come with terrifying risks. One miscalculation near such extreme gravity could compress years into seconds for those aboard, stranding them light years away from their intended timeline. The cruelest irony, dark energy might make escape impossible no matter how advanced the technology. As the universe expands, the space between superclusters stretches faster than any ship could hope to traverse. Civilizations that delay their exodus too long could find themselves trapped in an isolating bubble of space, their galaxy cluster irrevocably cut off from the rest of the cosmos. The Great Attractor would loom ever larger in their skies, not because they're moving toward it, but because everything else has vanished over the horizon of an accelerating universe. Yet for those undeterred, the attractor could also be an opportunity. Its immense gravity might serve as a slingshot for ambitious voyages, flinging ships toward distant superclusters with velocities unattainable any other way. Or perhaps its dense core holds resources unimaginable in the sparse galactic outskirts, exotic matter, primordial energy, even gateways to other cosmic epochs. The same force that threatens to imprison civilizations could become the universe's greatest highway if only someone learns to ride its currents. This cosmic balancing act between escape and surrender, danger and opportunity, mirrors the choices all intelligent life must face. Do we fight the universe's currents or learn to flow with them? The Great Attractor, silent and unseen, may one day force that question upon us, and the answer could define not just humanity's future, but the fate of every civilization drawn into its irresistible embrace. At first glance, the Great Attractor might sound like the ultimate black hole, an invisible cosmic vacuum with gravity so strong nothing escapes, but the truth is far stranger. While supermassive black holes like Sagittarius, a star at our galaxy's center, crush millions of suns into a singularity smaller than a grain of sand, the Great Attractor sprawls across hundreds of millions of light years, its gravity woven from thousands of galaxies, dark matter, and hot gas clouds. It's like comparing a whirlpool to an entire ocean current. One concentrates unimaginable force into a tiny point, while the other moves entire galactic neighborhoods with the slow, inevitable pull of sheer cosmic bulk. Take the largest known black hole, Ton 618. With 66 billion solar masses, its event horizon could swallow our solar system whole, yet its gravity fades to insignificance just a few light years away. The Great Attractor, by contrast, exerts measurable influence across 150 million light years, bending the paths of galaxies the way a mountain range diverts weather patterns. That's because black holes dominate through density, their mass packed into near infinite smallness, while the attractor rules through sheer scale, its gravity amplified by volume rather than compression. Here's where things get counterintuitive. If you replace the Great Attractor with a single black hole of equivalent mass, say 50 quadrillion suns, you'd face a cosmic paradox. A black hole that massive would have an event horizon spanning thousands of light years, making it brighter than all the stars in the observable universe combined as infalling matter heated to extreme temperatures. Yet the attractor emits no such light. Its gravity signature matches something far more diffuse, a sprawling metropolis of galaxies and dark matter, where the nearest star might still be tens of thousands of light years from its neighbor. This invisible architecture explains why we feel its pull long before we see its structure, like sensing a storm's winds before spotting the clouds. Another key difference lies in destruction. A black hole's tidal forces would spaghettify stars long before they crossed its event horizon. But galaxies drifting toward the Great Attractor don't disintegrate, they merge. Within its core, astronomers have observed colossal galaxy collisions, where gravity weaves spirals into ellipticals over billions of years without the violent shredding black holes inflict. It's the distinction between falling into a woodchipper versus joining a slow-motion traffic jam on the grandest cosmic freeway, yet both share eerie similarities. Like black holes, the Great Attractor warps spacetime around it, creating gravitational lenses that distort the light of background galaxies. And just as black holes anchor their host galaxies, the attractor anchors the Laniakea supercluster, serving as the gravitational heart around which half a quadrillion stars orbit. The critical difference: scale. Where black holes are cosmic potholes, localized pits in spacetime, the Great Attractor is more like a continental shelf, tilting the fabric of reality across intergalactic distances. This distinction matters because it reveals how gravity operates at different cosmic magnitudes. Black holes show us gravity's power to annihilate, while the Great Attractor demonstrates its power to organize. One shreds stars into oblivion, the other sculpts the universe's largest structures. Both remind us that gravity is more than a force, it's the architect of reality, shaping everything from the tiniest particle's path to the grandest flows of galactic superclusters. And somewhere between these extremes, in the interplay of density and distribution, lies the secret to why our universe looks and moves the way it does. The Great Attractor's enigmatic pull hasn't just captivated scientists, it's fueled the imaginations of storytellers, becoming a recurring motif in science fiction that taps into our deepest cosmic fears. From blockbuster films to cult novels, this invisible force has been reimagined as everything from a gateway to other dimensions to an existential threat lurking just beyond the stars. Christopher Nolan's Interstellar flirted with the concept, portraying a universe where gravity transcends time and space, bending reality itself. While the film never names the Great Attractor directly, its vision of a tesseract built by future humans inside a black hole echoes the same awe and terror the real cosmic anomaly inspires. A force so vast it twists the rules of physics into something almost mystical. Video games have taken even bolder liberties. The cult classic Destiny universe features the Darkness, an ancient enemy drawn to massive gravitational anomalies, with lore hinting at a hidden power at the galaxy's center, a clear nod to the attractor's real-life pull. Meanwhile, indie darlings like Outer Wilds weave it into their narratives more subtly, casting it as a cosmic mystery players must decode before their solar system collapses into its grasp. These stories resonate because they mirror our real scientific quandaries. Is the attractor a natural phenomenon, or could it be something far more deliberate? Fiction loves to hint at answers science hasn't found, turning the unknown into a canvas for existential dread or wonder. Literature, too, has seized on the attractor's potential. Alastair Reynolds' Revelation Space series envisions it as a graveyard for ancient civilizations, a place where galaxies converge and time distorts under gravitational strain. In Liu Cixin's The Three-Body Problem, it's reimagined as a trap set by hostile aliens, a cosmic snare pulling unsuspecting worlds toward annihilation. These narratives thrive on the same unease that haunts astronomers, the sense that we're being dragged toward something we can't see or understand. The attractor's real invisibility makes it the perfect antagonist. It's a villain that doesn't need a face, just an irresistible, inexorable pull. What makes these portrayals so compelling is how they mirror humanity's relationship with the cosmos itself. The Great Attractor is rarely just a plot device, it's a metaphor for forces beyond our control, whether fate, entropy, or the universe's indifference. Sci-fi amplifies our instinctive reaction to the real discovery, that we're not still, not central, but caught in a current we didn't choose. And perhaps that's why these stories linger long after the credits roll or the last page turns. They let us grapple with the attractor's true terror, not that it might destroy us, but that it reminds us how small we are in a universe that moves according to rules we're only beginning to glimpse. Does the Great Attractor reveal a hidden design woven into the fabric of the cosmos, or is it just a fleeting ripple in an ocean of chaos? This cosmic behemoth forces us to confront one of humanity's oldest questions, whether the universe operates on randomness or follows some deeper, unseen script. On one hand, the precise alignment of galaxies streaming toward this gravitational focal point feels almost intentional, like pieces on a chessboard moving toward checkmate. The sheer scale of this convergence, millions of galaxies drifting in unison, suggests a choreography so vast, it's hard not to wonder if we're witnessing the universe's version of fate. Yet there's another way to see it. What if the Great Attractor is just a temporary density fluctuation, a cosmic eddy that will eventually dissipate as dark energy stretches space beyond gravity's reach? Imagine a whirlpool forming in a bathtub. For a moment, it dominates, drawing everything toward its center. But once the water stops swirling, the structure vanishes without a trace. Could the attractor be the same, billions of years from now, as the universe expands and matter spreads thinner? Its gravitational grip might weaken until it's just another ghost in the cosmic background, its purpose faded into oblivion. This duality touches on something profound about how we perceive patterns. Human brains are wired to seek order. We see faces in clouds and constellations in stars. The Great Attractor's pull feels meaningful because our minds crave narratives where none may exist. But science reminds us that gravity needs no grand plan to operate. Galaxies fall toward the attractor not because the universe demands it, but because mass bends spacetime, and bent spacetime tells matter how to move. It's a dance without a choreographer, where the steps emerge from simple rules playing out over incomprehensible timescales. Still, the philosophical implications are irresistible. If the universe has preferred directions, currents like the attractor's pull, does that make it less random than we thought? Ancient cultures saw celestial motions as evidence of divine will. Modern cosmology replaces gods with gravity, but the awe remains. There's a haunting beauty in the idea that our galaxy, along with countless others, is caught in a flow older than Earth itself, riding a tide set in motion when the cosmos was young. Whether that tide leads somewhere meaningful or nowhere at all depends on whether you think meaning requires intention, or if the sheer immensity of the process is enough. Perhaps the truth lies between these extremes. The Great Attractor may be neither destiny nor accident, but a glimpse into how complexity arises from simplicity. Like snowflakes forming unique patterns from basic physics, cosmic structures emerge from gravity's slow work, creating temporary order against entropy's relentless push. We're privileged to witness this moment long enough for galaxies to cluster, but before dark energy scatters them beyond reach. In that sense, the attractor isn't just a force. It's a reminder that the universe is always becoming, and we're here just long enough to ask why. Among the swirling theories about the Great Attractor, one persistent myth paints it as a doomsday device, an all-consuming universe killer on a collision course with Earth. The truth is far less dramatic. While its gravity is undeniably powerful, spanning millions of light years, the Great Attractor isn't a cosmic vacuum cleaner sucking everything into oblivion. Think of it more like a gravitational landmark, a mountain in the cosmic landscape that galaxies flow around, not toward with catastrophic intent. The Milky Way's journey toward it resembles a leaf floating down a river, not a hapless insect spiraling into a drain. Even if we were headed straight for its core, which we're not, the distances are so vast that any hypothetical arrival would take hundreds of billions of years, long after stars like our Sun have burned out. Then there's the exotic speculation that the Great Attractor could be a portal or wormhole to another dimension. While wormholes are mathematically possible in Einstein's relativity, there's zero observational evidence that one lurks behind the Milky Way's dust clouds. Wormholes require conditions so extreme, negative energy, infinite stability, that even if one existed naturally, the Great Attractor's diffuse structure couldn't sustain it. Its gravity comes from the combined mass of thousands of galaxies and dark matter, not a singularity's infinite density. The real science is compelling enough without invoking science fiction. This cosmic anomaly is reshaping our understanding of gravity and large-scale structure, not bending reality into a gateway. Another common mix-up, confusing the Great Attractor with a supermassive black hole. While both involve immense gravity, black holes concentrate mass into infinitesimal points, whereas the attractor spreads its influence across a region larger than 10,000 Milky Ways. A black hole's event horizon traps everything nearby. The attractor merely nudges galaxies along gentle arcs over eons. Even the largest known black holes are mere pebbles compared to this sprawling gravitational watershed. Perhaps the most pervasive myth is that the Great Attractor is unique. In reality, superclusters like Shapley and Hercules exhibit similar, sometimes stronger gravitational pulls. Our local cosmic web is dotted with these hubs, each a nexus where galactic filaments converge. The attractor stands out simply because it's our nearest supercluster core, not because it's anomalously powerful. This misconception reveals a very human bias. We tend to assume the phenomena affecting us must be extraordinary, when often they're just our local corner of a universe teeming with equally marvels. Dispelling these myths isn't just about setting the record straight. It's a reminder that the universe's true wonders need no embellishment. The Great Attractor's real story of dark matter's invisible architecture, of galaxies moving in silent concert, of space-time bending on scales we're only beginning to map, is more awe-inspiring than any doomsday fantasy. By stripping away the fiction, we uncover a deeper truth. The cosmos is strange enough without inventing dangers or shortcuts. The mysteries that remain, like dark flows, unexplained speed, or the attractor's hidden core, are puzzles waiting for evidence, not leaps of imagination. And that's where the real adventure lies. What if you could contribute to unraveling the Great Attractor's mysteries without needing a PhD or a telescope? The truth is, modern astronomy isn't just for professionals. Ordinary stargazers are making groundbreaking discoveries through citizen science projects. Platforms like Zooniverse's Galaxy Zoo have transformed cosmic research into a global collaboration, where anyone with an internet connection can help classify galaxies, track cosmic flows, and even uncover hidden structures lurking behind the Milky Way's dust. It's like being handed a key to the universe's backstage, where your clicks and observations become part of real scientific papers. Here's how it works. Telescopes like the Sloan Digital Sky Survey capture millions of galaxy images, but there's a bottleneck. Computers struggle to distinguish spiral arms from elliptical blobs or spot oddities like merging galaxies. That's where human intuition shines. By logging into Galaxy Zoo, you're presented with real telescope images and asked simple questions. Does this galaxy have a disk? Are there signs of collision? Your answers help train AI and flag anomalies professionals might miss. Already, volunteers have discovered rare green P galaxies and Hanny's Vorwerp, a cosmic ghost illuminated by a quasar's long-dead light. The next oddity could be your click away, buried in data too vast for any one team to sift through alone. But galaxy classification is just the start. Projects like Radio Galaxy Zoo dive deeper, mapping how supermassive black holes influence their surroundings by linking radio emissions to visible galaxies. Others, like Backyard World's Planet 9, let you hunt for hidden objects in our own solar system. The data you help process could reveal dwarf galaxies orbiting the Milky Way, clues to how the Great Attractor's gravity tugs on our local cosmic neighborhood. It's cosmic detective work where every participant gets a badge, not as a spectator but as part of the team. What's thrilling is how these efforts amplify professional research. When astronomers studied the Great Attractor's pull, they leaned on collective data from thousands of volunteers who'd painstakingly measured galaxy shapes and positions. Your contributions might not land you a Nobel Prize, but they could nudge a scientist toward the next big breakthrough, like spotting a previously unknown galaxy cluster hidden behind the zone of avoidance, or refining the map of dark matter filaments that guide the attractor's flow. The best part, you don't need fancy equipment or prior knowledge. Many projects include tutorials that turn beginners into proficient classifiers within minutes. Schools, libraries, and even coffee shops have become hubs for crowdsourced cosmology, where a lunch break can double as a cosmic exploration session. For teachers, it's a goldmine. Students can analyze real data instead of textbook examples, sparking passions that might one day fuel careers in astrophysics. So while the Great Attractor's secrets may seem locked behind high-tech observatories and supercomputers, the truth is more democratic. Every time you log in and tag a galaxy, you're adding a stitch to the tapestry of human knowledge, helping science peel back another layer of this cosmic enigma. And somewhere in that vast dataset, your curiosity might be the spark that lights the way to the next great discovery. The Great Attractor may be one of the universe's most compelling riddles, but it's far from the only one. Lurking in the shadows of our cosmic understanding are even deeper mysteries, each intertwined with the attractor's pull in ways we're only beginning to unravel. Take dark matter, the invisible glue holding galaxies together. While we've mapped its gravitational fingerprints for decades, its true nature remains elusive. Is it a sea of undiscovered particles, a flaw in our understanding of gravity itself? The Great Attractor's unexplained mass could be the key. Its gravitational might far exceeding what visible matter should allow, hinting at dark matter's hidden architecture on scales we've barely probed. Picture an iceberg. The attractor's galaxies are just the tip, while beneath the cosmic surface, dark matter's invisible bulk could span distances that redefine our maps of the universe. Then there's the enigma of quantum gravity, the holy grail of modern physics. Einstein's relativity explains the attractor's large-scale pull beautifully, but near its core, where densities reach unimaginable extremes, spacetime might warp in ways relativity can't predict. Some theories suggest that in such chaotic environments, quantum effects usually negligible on cosmic scales could twist gravity into strange new behaviors. Imagine the attractor as a cosmic lab where space itself frays at the edges, offering glimpses of a deeper theory that unites the quantum and the cosmic. If we could peer into its heart, we might spot anomalies, subtle tremors in the fabric of reality that reveal how gravity truly operates when pushed to its limits. And what of dark energy, the universe's most perplexing force? While it drives galaxies apart on grand scales, the Great Attractor represents gravity's stubborn resistance, a reminder that even as the cosmos expands, some structures cling together against the tide. This tug-of-war raises profound questions. Is dark energy constant, or could its strength fluctuate over time? If it grows weaker, the attractor's grip might dominate locally far longer than we think. If it strengthens, even superclusters could be torn apart. The attractor isn't just a destination. It's a battleground where the universe's two most mysterious forces clash, and the outcome could reshape the fate of everything. Beyond these lie even wilder possibilities: cosmic strings, hypothetical cracks in space-time left over from the Big Bang, or hidden dimensions curling around the attractor's core. Some theorists speculate that the strange coherence of dark flow, with galaxies moving in unison beyond the attractor's reach, might hint at a reality far larger than our observable universe. Could our cosmos be a bubble among others, with the attractor caught in the gravitational tides of a neighboring universe? It sounds like science fiction, but the edges of our knowledge always do until they don't. The beauty of these unsolved puzzles is how they feed into one another. Dark matter's distribution might explain the attractor's pull, which in turn could reveal clues about dark energy's true nature, all while testing the limits of relativity and quantum mechanics. Every mystery is a thread in the same cosmic tapestry, and pulling on one inevitably tightens the others. As we chase the Great Attractor's secrets, we're not just mapping a single anomaly, we're piecing together the operating manual of reality itself, one revelation at a time. The journey doesn't end with understanding where we're being pulled. It begins with asking what else is out there waiting to be discovered in the dark. From its shadowy grip on galaxies to the way it warps time itself, the Great Attractor stands as one of the universe's most humbling mysteries, a reminder that even in an age of space telescopes and supercomputers, the cosmos keeps its deepest secrets close. We've traced its gravitational fingerprints across hundreds of millions of light years, watched galaxies stream toward it like leaves caught in a cosmic river, and yet its true nature remains just out of reach. Is it a dense nest of dark matter, a signpost to something even larger, or a flaw in the very fabric of space-time? Every answer we uncover only leads to more questions, and that's the beauty of it. This isn't just about mapping a distant anomaly. The Great Attractor represents something far grander: humanity's relentless drive to make sense of the unknown. For centuries, we've looked up at the stars and wondered what forces move them. Now, we're not just observers, we're detectives piecing together clues written in gravity's invisible ink. Every galaxy's motion, every warped photon of light, is a breadcrumb leading us closer to understanding how the universe organizes itself on scales that defy imagination. And while we may never reach the attractor's core, the pursuit itself transforms us. It stretches our minds, challenges our theories, and humbles us with the realization that we're riding a tiny speck of stardust through a cosmic current older than time. So what's next? The mystery doesn't end here. With next-generation telescopes peeling back the Milky Way's dusty veil and citizen scientists classifying galaxies from their living rooms, we're on the verge of revelations that could rewrite astrophysics. Maybe we'll find the attractor's hidden heart, or stumble upon something even stranger lurking in its shadow. That's the thrill of exploration. The universe always has another surprise waiting just beyond the edge of our understanding. As you look up at the night sky tonight, remember this: you're not just staring at stars. You're witnessing a grand, unfolding story, one where galaxies dance to gravity's tune, where space-time bends like a hall of mirrors, and where invisible forces sculpt the universe in ways we're only beginning to grasp. The Great Attractor isn't just pulling galaxies, it's pulling us not toward doom, but toward discovery. So stay curious, keep questioning, and never stop marveling at the fact that we live in a universe wild enough to hide giants in its shadows. After all, the next great cosmic revelation might be just one observation away.